वेलकम वेलकम वेलकम। तो आज हम जानेंगे बफरिंग कर्व्स ऑफ मिल्क के बारे में। तो हम जानते हैं कि हमारे दूध के अंदर कुछ ऐसे कंपोनेंट होते हैं जो कि बफरिंग कैपेसिटी शो करते हैं। तो अगर पूछे तो एनीबडी आस्क यू दैट कौन कौन से ऐसे कंपोनेंट हैं जो कि बफरिंग इफेक्ट शो करते हैं, तो पहले आपका साल्ट्स आता है। साल्ट्स के अंदर आपका कैल्शियम फॉस्फेट है, सिट्रेट है और बाइकार्बोनेट है। इसके अलावा एसिडिक और बेसिक एमिनो एसिड्स भी होते हैं प्रोटीन्स के, जो कि बफरिंग कैपेसिटी को शो करते हैं। मेनली जो कैसिन के जो एसिडिक और बेसिक एमिनो एसिड्स हैं वो आपका बफरिंग इफेक्ट को शो करते हैं। ठीक है, तो आपका जो स्लाइड पे आपको एक टाइट्रेशन कर्व दिख रहा है, तो इसमें हमने टाइट्रेशन कैसे किया, जैसे हमारी इनिशियल पीएच यहाँ पे 6.6 है, उसको हमने 0.5 नॉर्मल एचसीएल से टाइट्रेट करके पीएच 3 तक लाए। तो देख सकते हैं आपका कर्व कैसे आ रहा है। बफरिंग, ये जो कर्व है बफरिंग कर्व किसके बीच में बना हुआ है, पीएच एक्स एक्सिस पे लिया हुआ है और बफरिंग इंडेक्स जो है आपने वाई एक्सिस पे लिया हुआ है, डीवी बाई डीपीपीएच। तो आपको मैंने बताया था कि बफरिंग कैपेसिटी और बफरिंग इंडेक्स दो टर्म होती है। बफरिंग कैपेसिटी का मतलब होता है कि अमाउंट ऑफ मोलर अमाउंट ऑफ स्ट्रॉन्ग एसिड और स्ट्रॉन्ग बेस रिक्वायर्ड टू चेंज द पीएच ऑफ 1 लीटर ऑफ सोल्यूशन बाय 1 यूनिट। ये आपकी बफरिंग कैपेसिटी की डेफिनेशन है कि कितनी मोलर क्वांटिटी आपको स्ट्रॉन्ग एसिड या स्ट्रॉन्ग बेस की चाहिए किसी भी पीएच की पीएच टू चेंज द पीएच ऑफ 1 लीटर ऑफ सोल्यूशन बाय 1 यूनिट। 1 लीटर सोल्यूशन की पीएच अगर आपको 1 यूनिट चेंज करनी है तो कितना अमाउंट ऑफ स्ट्रॉन्ग एसिड या स्ट्रॉन्ग बेस लगेगा, उसको उसी को हम क्या कहते हैं, बफरिंग कैपेसिटी कहते हैं। और बफरिंग इंडेक्स भी एक तरह से सेम ही टर्म है, लेकिन इसको डिफाइन करने का तरीका थोड़ा सा अलग है कि टू डिफाइन द इंक्रीज इन द अमाउंट ऑफ acid or base to the pH variation, that is differential ratio of the increase in the acid or base to the pH variation, that is buffering index. So here we can see that buffering index I have taken on the y-axis and pH I have taken on the x-axis. Now pH here it is 6.6, so I have titrated the milk from pH 6.6 to pH 3.3 using 0.5 normal HCl and then back titrated it to pH 11 using 0.5 normal NaOH. So here we can see that it is we have titrated it back using 0.5 normal, and that here we can see that there is marked hysteresis, that they are not matching, so there is hysteresis there. So there is marked difference between the forward titration curve and the backward titration curve. So this is the one technique we have used, wherein first we have titrated the milk from pH 6.6 to 3 and then back to 3.11, and this is the way the titration curve will appear. Okay, so here we can see that when the milk is being titrated to pH 11, so using 0.5 normal natural, we will see that at 5.5 there is minimum buffering capacity and there will be highest buffering capacity at pH 6.3. Now why this highest buffering capacity is there at 6.3? Now see this reaction, 3 calcium ion plus 2 phosphate ion give you calcium phosphate plus H plus ion. So this is the this is a very important reaction, as I used to write always. So here in this side, if we have increasing the acidic condition, so reaction will move toward the left, and if we are increasing the basic condition, then the reaction will move toward the right. So since here we are increasing the basic condition, so it is expected that H plus ion will increase. Now since the H plus ion is increasing and you are adding the base NaOH, you are adding, so this H plus will countering the titration, that countering the NaOH during the titration, so showing the buffering effect. So that the maximum buffering effect is having at pH 6.3 because of the formation of colloidal calcium phosphate. So this is for colloidal calcium phosphate with the release of H plus ions, which will be countering the NaOH ion which is being added during the titration. So maximum buffering capacity will be at pH 6.3. So see, you can see the graph I am again showing. So here your pH 6.6 to pH 3.3 titration curve is showing, and 3 to 11 the curve is showing. And then if you're titrating it using 0.5 normal NaOH, you will see that in the back side when we're back titrating, that minimum buffering capacity will be at pH 5.5 and maximum will be at 6.3. And maximum why it is maximum here, because of the formation of colloidal calcium phosphate and the release of H plus ions, which will be showing the buffering capacity. Okay, so one point here to mention is that the forward and backward titrations are having marked hysteresis. So there is marked hysteresis between the forward and the backward curves. Okay, just this is the just to tell you that how the buffering capacity is changing with respect to pH during the titration. When we are changing the pH from 6.6 to pH 3 and back 3 from 3 to back to 11, then how the titration curve or the buffering index is changing with respect to pH, that is known as the buffering curves. So this is one technique. So in another technique, what we are doing is, first we are titrating the milk from pH 6.6 to 11 using 0.5 normal NaOH, and then we are back titrating it to pH 3 using 0.5 normal HCl. So it's written also here that buffering comes from milk titrated from initial pH 6.6 to pH 11 with 0.5 normal NaOH and back titrated to pH with 3 with 0.5 normal HCl. So here this is the titration curve. Now here we can see that as we are titrating the milk in the forward direction using the 0.5 normal NaOH, we see that minimum buffering capacity is at pH 9, and after 9 mainly after 10 the buffering capacity is increasing, and this is mainly because of the lysine and carbonate. So written on the slide that lysine and the carbonate, the buffering capacity is there after pH 10 because of lysine and the carbonate. So at high pH the buffering capacity is because of the lysine and the carbonate. Okay, and then we are back titrating it, and we can see here that maximum buffering index is shown at pH 5.1. So especially after 5.4 the buffering index is increasing. So here after 5.4 it is increasing up to 5.1. Now this why this there is buffering capacity. So we know that we are now, since we are back titrating, so we are adding HCl. So since we are adding HCl, so we are increasing the acidic conditions. So this reaction here in this reaction will proceed toward the back. So since there will be dissolution of calcium phosphate, so this calcium phosphate will dissolve and we'll have the phosphate. So this phosphate, when we are adding the H plus, so we are decreasing the acidity, we are adding the HCl. So H plus this will be combining with the H plus to form the dihydrogen phosphate. So monohydrogen phosphate to dihydrogen phosphate. So this will be acting as a buffering system, and that is why we are having maximum buffering capacity at 5.1. And another point to write here over is that so forward and backward titration is having little hysteresis. So the technique which we have used earlier, wherein we first acidified and then back titrated, here in this we first made the milk alkaline and then back titrated to pH 3. So techniques are different, so your hysteresis is also different. So here little hysteresis is there, and in the previous we have seen that there is marked hysteresis, that is marked differences between the titration curves. So here only little hysteresis is there. So here I will show you that here only little hysteresis, and the way the titration curves are behaving, that I have explained you, that you have to write that from 6.6 to pH 11 the titration minimum is at 9, and after 10 the amazing buffering components are the lysine and carbonate. And why it is having the maximum at pH 5.1 buffering capacity, it is because of the dissolution of calcium phosphate, and this phosphate which is being produced will be reacting with the H plus which is being added, and then we have the dihydrogen phosphate, and then these will be acting as buffering, showing the maximum buffering index at 5.1. So these are the buffering curves of milk to show that the way you are titrating the milk, the technique which you are using, or the forward or back titration you are doing, and there will be hysteresis, and what are the components, what are the different components which are contributing to the buffering capacity at different pH ranges. This we must know. Okay, so these two are simply the buffering curves of milk. Thank you.